So I'm Stuart Williams. I'm a software engineer at Pivotal. I've been with the organization that became Pivotal. A bit of VMware before that was vFabric and Spring Source for 4 years. I was a consultant until 18 months ago when I joined an engineering team, became project lead for a project called RTI. So a little introduction about what the talk is and what my slightly bombastic title, 1 million events per second, is all about. We built a product. We started building a product from a proof of concept that's a couple of years old. We started building it as a product around 18 months ago. It uses all Pivotal products, a lot of open source, a lot of Spring, and we learned a lot of lessons about how to build software with these things along the way that we, in the engineering team, thought we could if we could share with you at the conference. We found a few limitations in bits of the application frameworks and the products that we were using, and some room for improvement. And I'm pleased to say that we are able to address those and things go faster, which is good for you. In some cases, things go a lot faster. So what is the product? It's built with the Spring IO platform. So we use boot, we use Spring data, various incarnations of Spring data. We use Spring integration, Reactor, Spring AMQP, Spring expression language, and Spring shell, and a little bit of Groovy. We use both RabbitMQ and Gemfire. And we use those in slightly different ways, and I will explain where we're using each of those and why they're in that part of the application. Before I go any further, there's a couple of questions that I thought I'd ask you first. As a consultant, I was a little bit surprised sometimes that when I found people didn't know about a project called Spring Integration. So if you could put your hand up if you've heard of Spring Integration. So that is about half the room. Put your hand up if you work for Pivotal. Yes, that's about a third of the room. If you don't work for Pivotal and you've heard of Spring Integration, have you ever tried to use it? And have you tried to use it in production? Can I see some hands? Okay, so that's maybe 10, 15 people. And lastly, the same questions for Reactor. Apart from the conference today, before the conference today, had you heard of the Reactor project? Okay. Cool. Anybody tried it in production? No hands, interesting. Okay. So some of the people who work on the projects and some of the projects I'm going to talk about are in here today, and I'm going to keep pointing them out. There's no doubt they'll have some questions at my expense at the end. So RTI, what is RTI? RTI stands for Real-Time Intelligence, and it is a stream processing application, specifically in the telecom space. It's built to process data that comes off mobile phone network devices, so cell phone devices. The application has a couple of specific features. Once we're processing the data, we do location-based services. We look to see the geographic location of various pieces of information in the data and do operations on those. In some case, that means producing streams and queues of messages that are associated with a geographical area, which have a number of different properties to them. And the other thing we're able to do is do a number of different types of analytics on features of the data. And for example, that can tell a cell phone network operator the state of their network health and do that in near real time, which is not a capability that most operators have right now. Telecom network data is quite interesting. It's got quite a rich data model. There are a number of identifiers that you'll probably be familiar with. If you think about your cell phone, you have an IMEI device, IMEI ID. There are a number of other identifiers depending on what network type you have. So for GSM, there's subscriber IDs, things called IMSIs, and a number of other features. But there's also quite a lot of additional data that comes off the different network protocols. So think 3G voice, 3G data, 2G voice data, LTE, that kind of thing. There are differences between each of the voice and data protocols, and there's differences between, say, 2G and 3G. You can imagine that as the protocols evolved, the data became more rich and has more properties to it. There's two flavors of data from the high-level view. We refer to as user plane and control plane data. Control plane data is the metadata. So when you make a call on your cell phone, we get an event that says you started to make the call. We get an event that says the call ended or you switched cell tower. That's the metadata, that's the control plane. The user plane is the real data that's transmitted. So if you're downloading a web page, the data that is being downloaded exists in the user plane of the data. So it's two separate streams from the network operators. And right now, RTI processes only the control plane data. The user plane data is 30 times more of that data is what the operators tell us. And you'll see why that's important in a second. So we have this product deployed in a number of places in EMEA, and we've deployed it in Australia as well. And we see typically an average, or rather a baseline rate of 100,000 events per second of this control plane data. A daily peak can be 120K per second, and we see a million or more in an annual peak. So that's the 1 million I can get to. Just to put this in context, Twitter, by their own statistics, whereas a lady tweeted the information about what their ingest rates are 6K per second, 9K daily average, and 30K for large events. So there is quite a significant order of magnitude difference. The RTI application is more akin to a trading application in a bank. But we have a number of other properties which make it slightly different for us. The trading applications usually see payloads of very similar sizes. Of course, I don't think it's fair to compare ourselves entirely with Twitter. We don't have to do distributions to the millions of followers for each event that come out, but we do see some fan out inside our application that we have to take care of and engineer around. So what are the load characteristics? We have a relatively small number of inbound connections into the application. We do see high rates consistently and microbursts of some multiples occasionally. And the variable payload size goes from in the 200 byte range to the 300 kilobyte range, which makes for an interesting tuning problem on the network. And as I was saying, the internal fan out on multiple events is things like in part of the application where we start to do location-based services. If a given event appears to be in a geofence, it may appear in multiple geofences, so that will produce multiple events off the back of that single input event. And as I'll explain a little bit more in a minute, the analytics part of the application may produce hundreds or more of additional events from a single input event. So there's our 100,000 events per second order of magnitude. I thought it would be worth highlighting what that means. 100,000 events per second is 8.5 billion events per day, which, as we discovered, makes an integer counter roll over within a couple of days. We process 400 megabits per second of raw data, which means that if there's any variation in that load, we need 10 gig network cards right the way through the infrastructure to make sure we stay on top of that. Otherwise, we're effectively providing our own denial of service. Any accidents on the logging front, any errors, can blow away a disk if you don't control the amount of log file. And if you do control the amount of log file, your log files are handily rolling over, then the original error may disappear quite quickly because you've rolled all your log files over. And we've certainly seen during the development of the product, the original source of an error message disappear within a second or so. Inside the application, I say we're a stream processing application. There are a number of types of queue inside the application. If any of those queues fail or fill, the application can fail quite quickly. There's a number of strategies you can use to get around this, but ultimately, if you run out of space, you're dead. So what does RTI look like? I have a nice, pretty, multicolored diagram. There are two major halves to the application. The source data is in one data center in our first deployment, and the business activities are in a second data center. You can imagine that all of your cell phone data, the data you guys are producing right now, even your phone's not being used properly, hopefully, are producing events every few minutes, a few events per minute, in fact. And we see all of that. Now, the source of that data on the edge of the customer's network is obviously sensitive in terms of privacy. So that data center is secured. We anonymize data as it passes through that data center, and there are lists of opt-ins where we decide whether we're able to look at that source of the data and process it any further in the system. So on the left-hand side of the diagram is really all about ingest. So can we get the data from the network sources and into our compute grid, which is built on Gemfire, and start processing on that data. So we want to get it into the grid as fast as we can. And then the data is put on a wide area network queue as a feature of Gemfire. There are a number of different ways of implementing this. Gemfire has a specific way, which batches the data up and passes it over to the second data center. And the second part of the application, the data center, is split into this two halves. It's really, every node does both pieces of work, but logically they're quite distinct inside the application. So we do a piece of analytics, and we do a lot of distribution. So we have the concept of the fire hose out. The data, as it's processed through the application, is fed to a big data store or a database. And there are a number of different ways to process that. So we have two feeds out, primary feeds out there, and a third feed, which is our location-based services feed, and then the analytics processing, which is ranges of metrics that are also output from to file or to one of our Rabbit brokers. So what are the architectural challenges here? As soon as we've got control of some of the data, we need to start getting it into a reliable piece of infrastructure as soon as possible. So where we have any data that's in memory in part of the application, we need to hold that for the minimum time, and we need to not keep it lying around. So unfortunately, this is a contradiction to contrary influence on one of the strategies that we use to ensure that throughput stays up. So we try to batch data whenever we go to the network, and that means keeping data in memory for a short period of time where it's not reliably held. It's pretty hard to do that, so there's a trade-off we have to make right now. And what are the infrastructure considerations? So obviously we need to have some compute available. It turns out that compute's readily available is pretty cheap, and memory is readily available. In fact, because we're processing this data in a relatively short space of time, we don't really use a great deal of memory to do so. And I mentioned earlier disk. You do need to have plenty of disk to ensure that any log files are survivable, and in some cases some of our Gemfire application can overflow to disk. Well, a really big problem is the network. We are very sensitive to network bandwidth, and in fact much more surprisingly so than we thought we would be. John, who's sitting over there, is going to talk a little bit more about data in his talk, Big Data in Memory, which is later today. I'll keep plugging that, because we've worked with him on some of the technology to ensure that our byte sizes and payload sizes stay down. But that was a kind of really important part when we were passing data around in the application. So the ingester. Ingester is our first point of entry into the application. It's primarily a Spring integration pipeline. Starting on the left-hand side with the TCP server, we transform the bytes into a Java object, a POJO. We do some filtering, validation of the object. Do we have the right types of identifiers that will allow us to route it further down the application? And then we use a Reactor stream. And I'll explain why in a minute we ended up using the Reactor stream. And then there's a Gemfire client. The Gemfire client is a client cache, but we're really only using it as a very non-caching entry point into the Gemfire grid, because it maintains connection pools to each of the Gemfire servers, and it has a feature called microbatching in the Gemfire client, which allows us to do a single put all into the region, which is a map, and have the Gemfire client do a distribution to each of the nodes, single hop. So we minimize the amount of network traffic to get the target data into the sharded, partitioned Gemfire regions on the servers. And it is a single process right now. We run 6 protocols in a production environment, so 2G, 3G, and 4G, and in another deployment we support things like Radius. We are able to configure, depending on resource availability, so we can run multiple ingesters, maybe different protocols for different ingesters. So we have the ability to support HA and load balancing to some degree, but really we don't need to. We are able to get into the right performance range for the characteristics, load characteristics we have with a single JVM process. I'm not going to talk about the whole of the application, the ingest grid. The ingest grid is really a big processing pipeline. It's not particularly interesting. I guess the more interesting points for me to explain are the different types of technology we use and why we made those choices. So in the analytics grid, because we have this multiple fan out around a single event, so multiple events are produced, we use the Reactor project's extremely optimal dispatching mechanisms. We do Spring expression language evaluation, and we do hundreds of expression calculations per event for all the different metric dimensions that were found in one of these objects. That data is collated across different nodes. So where there is a dimension, say, the number of calls in flight at the moment on a given cell tower, we have to collate that across all of the nodes in the system, because the sharded data sources, the protocol events as they're produced, are located on the user identifier to ensure that we do minimal reference data lookups and to minimize the network traffic between grid nodes. And then we output that to file or to AMQP. So you can imagine 100,000 events per second multiplied by hundreds. We're not going to be able to conveniently write that out one entry at a time to a file. So we use Reactor under the hood there as well, the Stream API, to do batching to make sure that we minimize our overheads going to the file system or to the network. Distribution grid, again, this one is a more Spring integration orientated component. It looks like a tree, really, so that one event in goes to many destinations out. There's some enrichment of that data and some filtering. Again, we use Reactor's Stream functionality to do batching. And in this case, all of that output goes to file, AMQP, and to JDBC as an option. And most of the logical operations that are going on in this part of the application are location-based services. Are you a member of a given set of privacy opt-ins or geographic opt-ins, geofences? And some of those lookups can be expensive. There are many sequential lookups in different sets. So we have some optimizations around that. So how do we get here is probably the more interesting part of the story for me. When we started out the project, we had some code already that had been used proof of concept. And we felt that in order to productize it and to maintain the flexibility that we knew we would need as the product evolved, that we'd like to rewrite substantial portions of it to use Spring integration and to use Spring infrastructure to start up the projects, different components, and to manage the application. So our first ingester solution was a Naïve proof of concept, build a pipeline, use the standard TCP adapters, transformer, filters, and outbound adapter. And of course, we needed some codecs to pass this data source from the telecoms network sources. And telecom network data is typically in exotic binary forms, very compact, very bandwidth sensitive. So we have had to do quite a lot of work to write parsers codecs for each of these different components. John will talk some more about the optimizations we've done in that space today. So here's our first Naïve proof of concept. Simple Spring integration pipeline per the integration graph that you find in STS. And it's a dead simple linear pipeline. And when we ran this, we found it didn't quite work as we liked. In fact, we pushed a 1.2 million event file through the pipeline. And we found when we put the profile on it, the reason that it was taking several minutes to push this data through was that message UUID generation was slow. Each Spring integration message has a UUID field as an ID field in the headers. And originally this was using random UUID. Hopefully if my demos work a bit later, I'll show you the difference when you use UUID generation. Spring integration, for all of the flexibility it offers, uses Spring expression language to resolve methods on the beans that do the logical operations. And we found that Spring expression language was slower, in fact, much more slower than we were expecting it to be in this space. And we also discovered that the standard channels were adding overhead, and of course, single event output, putting one object into Gemfire at a time, well, that sucked. So Mark II. We wrapped the pipeline as much as we could in an integration chain. The integration chain has a useful feature in that each message handler, each endpoint is mapped using a largely empty channel implementation between each point, so that all of the overhead we were seeing in the channels went away. And we were also able to implement the ID interface, ID generator interface. I thought I knew Spring integration pretty well at the time, and I discovered some new things. This is one of them. We decided to use specific endpoint interfaces, so we implemented Transformer rather than just using the Pojo approach, and Message Selector, which is the filter interface. And I will come back to the spell changes later. And we decided we would use an aggregator to build a batch so that we reduce the overhead of going to the network each time. This helped a lot, but it didn't really help us the amount we were expecting. We discovered that the specific interfaces weren't being recognized by Spring integration. And we found that the aggregator in particular was much slower than we liked. And we also discovered that the TCP inbound adapter was slower. We'd shaved some time off. We were able to see the profiler and performance improvements, but we were also able then to see where other places were revealed to be losing time. Gary Russell, the Spring integration project lead, is down here. He was the first person I went to. And fortunately, he was able to see some quick fixes. So in fairly short order, and many whiteboards later, my whiteboard started like this, and it got a bit more complicated, and then it started to look like this. And that's, I've got more photos of them, and probably too many to put in a slide deck, but there were a lot of these. And we have evolved over a couple of months' worth of working with the Spring team and the Reactor team, and doing our testing to a model that looks much more like this, incorporates some business logic that wasn't in there before. We see multiple protocol adapters on the left-hand side. Each of those is a TCP server for each protocol type, so we can manage each of those. We see quite a wide variation on the protocol adapters and the different amount of traffic that comes in from each protocol. You imagine the 3G protocols see quite a lot of data, and also a couple of the protocols present much larger payloads than the others. So having separate TCP servers gives us the ability to tune the behavior of those and add different numbers of thread pools for workers and so on. You can also see on this diagram that there is the batcher. The batcher is something I'm going to talk about in more detail, but we found an optimal way to build a batch and to push that batch onto the Gemfire client, and then we were able to, with reasonable degree of success, balance that against the connection pool that was in the Gemfire client. So our working version has Netty-based TCP and Reactor TCP endpoint, the ID generator interface, specific endpoint interfaces, chains, and Reactor stream-based batching, and a variety of improvements and enhancements that came into the frameworks and to support the loads that we were operating on. So that's a little bit of the story about the architecture, and alarmingly, I'm much further on in my talk than I was expecting to be. And at this point, I thought I'd switch from talking about the product and start to talk more about the improvements that we've seen in the framework and some of the detail and some of the things that you will now find in the framework and how you can use those, and hopefully a little bit of demonstration of the differences. So for performance, there's a couple of key changes in Spring integration that are worth mentioning, and a couple of things that you can see and use yourself today. And Spring expression language made a significant improvement in performance, and is guy responsible for that down the front. And hopefully I will show a little bit of Spring Expression Language and what the difference is there. I stood up in a meeting just over a year ago and explained to a number of our senior managers why we were taking Spring Expression Language out of the application for performance reasons. And there was a lot of grumbling and surprised faces in the room. And this produced a couple of conversations later, and I spoke to Andy, and he said, well, where's the effect of it? It's funny you should mention that, because I've been thinking about building a compiler for Spring Expression Language. I didn't really have a reason to do it yet. So he disappeared and worked with John, and came back a couple of months later with compilable Spring Expression Language. And boy, is it faster. Reactor is a relatively new project in Spring. It has some interesting features. It's largely built around the LMAX disruptor. I'm going to talk a little bit more about that in a second. The Reactor team is in here as well, I believe. Put your hands up. There they are, down there. And Spring XD is also worth talking about at this point because it benefits from a lot of the upgrades here. Spring XD, as if anyone's been to the Spring XD talks, you'll know that it's built largely around the Spring integration and batch frameworks for its operations on streams and on batch jobs. So some of these features that have evolved over the course of the last 18 months are making their way into this product. So Spring integration. The UUID generator is surprising for me, certainly. A new feature is in more recent version of Spring integration is the message builder factory, which allows you to modify the strategy for how messages are created inside each component, if a new component's made. And there's a new feature in the most recent version, which is a mutable message. So previously in Spring integration, messages were immutable, so a new one was created each time. And of course, that introduces some overhead, a little bit of garbage collection there. And there is obviously a benefit if you can tolerate mutable messages to being able to keep the same object and pass that around. There's also been some optimizations to the dispatcher inside the channels. Each channel uses a dispatcher to decouple the operation from each component over to the next component. And one of the optimizations that's probably worth mentioning is that if there is only a single subscriber to a channel, it will now, rather than iterate over the list of potential subscribers, it will now go directly to that one and execute against that. And that's a micro-optimization that makes a surprising difference when you have a complex application. Another feature of modifications to Spring integration earlier on was the Spring Expression Language parsing that was occurring in each of the endpoints we're doing that wasn't really being cached effectively, so it was being reevaluated, recreated every time, and that makes a difference to performance as well. And in Spring Integration 4.1, you'll find that there are long counters, which is good for us because we weren't able to see how much data we were losing. And interfaces are used directly. So if you're being specific about a specific component, Spring integration respects that. Right, let me see if I can get into my IDE. I don't know how well you'll be able to see this. I have a small application and some data source and a Spring integration pipeline, and I have an ID generator wired here with random UUID to generate the IDs. Yeah. Let's see if I can do that. Do you know what the shortcut is in this? Edit preferences. Yeah. Colors and fonts. Okay. Shows you I know, doesn't it? There we go. Better. Okay, so it's a little Spring Boot application. I'm going to start Reactor environment up. And here's my ID generator. Using a message builder factory. It's the default message builder factory. And you'll see in a second what I'm doing here with the codec. The data source itself is a big blob of bytes. Each byte is prefaced with a delimiter, an integer describing how long that is, the following payload, and that's marked all the way through the file. So I'm just going to pipe that data into my simple TCP server. Here's the server. It's a Reactor-based TCP server. So during the onInit method of my Spring integration endpoint using message producer support, I'm just going to define a simple netty TCP server. I have a dispatcher called work queue. There's the codec. I'm going to listen on this host and port. I'm using Java 8, which is cheating a little bit because we're not doing that in RTI yet. And I'm going to have a little counter. There's my message builder factory. I'm going to send that message there. The rest of the code is really just setters and the managed attributes to look at it in JMX. So starting the server. This is really the meat of the endpoint here. So you can see it's pretty easy to build a TCP server using Reactor and to embed that inside an endpoint. Let's clean up some of this. Here's my integration context. I've done the integration context in XML so that I can go like that, really. It looked better before, but here's my nice integration graph. There is another TCP connection factory in here, the standard TCP connection factory. It's running one port higher. And other than that, both of them pipe into a simple channel. And I set my fixed subscriber to false, which is one of the optimizations I was talking about. And really all I'm doing in this case is piping that to a counter and calling the counter and incrementing the counter. And the counter is exposed to JMX bean, so we'll be able to see that in JMC, which I will use for this purpose. And hopefully that will work. So let's find server. And run that as a Spring Boot application. Booty, booty, boot. And there's the server, there's the mbean server. I'm using mission control because I can, rather than visual VM in this case, because it means I can add a couple of extra counters as graphs. Add a chart. Go through that. There's my Spring integration stuff. There's a simple counter at the end. So I've got a counter on the way in and a counter on the way out. There's my data in channel. Here's my mean send rate. So I'm going to look at the channels. These are some of the metrics. I'm using Spring integration 4.1 here, so you can see that there's a long version of the send count there. I'm hopefully going to send that to, there we go, a couple of counters. So you should really only see one counter there when the load comes on, because they should be the same. And the mean send rate should show us how fast we're going. In my Tomcat talk yesterday, I said never do a performance test on your laptop, which is obviously now what I'm doing. So let's, this blew up earlier and I couldn't see why, so we'll see if this is really fast. If it's really fast, I mean it's not working. I'll make that bigger. And if it's really slow, it's doing what I expect it to do. Here goes nothing. Yeah, it's really fast, so it's not working. Let's try the other one. That's the Reactor-based TCP server. Well, that wasn't doing something. Okay, good. So there we go. Two counters, one slightly behind the other. The mean send rate is ticking up. It might take us a couple of attempts to get this to go any faster because the compiler kicks in and JIT does stuff. So normally on the second or third run we can see a bit of a performance benefit. Up we go, up we go. So this file has just over 500,000 events in the file, and it's going to be some time processing that. So it's taken 1 minute to get up to 350 events per second. It's still ticking up slowly. Okay, so I'm going to see if that's going to get us there any faster. It's taking its time. This is varied wildly between how fast it wants to go and depending on how much humming my laptop is doing. And my laptop is humming because it's driving that screen at the moment. So we might just stop that there and call it a day, 1 minute, 20 seconds. And let's see how much data we got through that. MB browser sent 70,000, so not very many at all. So if I kill off this one, where's my stop? Come on. Yeah, stop. I'm going to use a UUID utils from Reactor, which should be faster. And I'm going to replace this one with a mutable message builder factory. Other than that, we're all the same. Right, let's see if we can get this to go a bit faster. Oh, no, hang on. JMC's going to die on me. I can do that one too. Yeah. One's here, something here. That one's stopped. JMC has an unfortunate habit of dying quite badly if the other process stops. So let's just try this one and see if I can get connected. Up we come. Oh. Let's check which process ID that was. Oh, it's gone. Yeah, blown. There we go. Unfortunately, it doesn't remember the settings I had, so just bear with me while I put them back. One counter, visualize to chart 1. To chart 1. Message handler. I put these on different graphs because if one of the numbers increases above the others, it tends to obscure what the graph is doing. So there we go. So let's try again, same file. Oh, I got the wrong graph, hang on. In send duration, that's the wrong one. I thought that was low. Send rate. That's better. Ah, that's gone flat. So what's gone on there? Oh, it's finished already. So in much less time, in fact, those modifications have given us a significant performance improvement. So that's good. Let's run it again and see if we can get it to go faster. JIT kicks in and JIT does some interesting things to this stuff. So with a bit of luck, we'll see an even faster one the second time around. Yeah, 6 seconds. So once it's warmed up, we're processing 500,000 events, just over 500,000 events in 6 seconds on a single thread, which is not too shabby. And you can see the difference that made. Right? We could have left the original one running, and it would have been running here in for a few more minutes. The longest I had it running yesterday was 6 minutes. The other difference that's worth talking about here is that the benefits are not just how much data can you crunch, but really the CPU is doing no work here at all. It's barely touching the sides, which is, if you're running workloads in a cloud environment, then that's directly related to the expense that you're paying for your cloud environment. It also means that with low levels of resource utilization, you can soak up quite large peaks in load quite quickly. So if there's a short spike, then you can cope with that, certainly in terms of CPU. Okay.
Did you say the bottleneck was?
So there were a few bottlenecks that we iterated out of the application.
So like right now, if you were to try and max this out, what would the bottleneck be? You said
UUID generation is extremely expensive. The operations for rebuilding the message using different strategy there has an impact as well. Hey?
Which UUID utils are you using?
The one that's in the Reactor project. Uses a yeah. So Gary's just reminding me that in more recent versions of Spring Integration 4, there is the default random UUID algorithm is no longer used, and these are the feedback we were able to put into the project to fix these kind of things. So I have another one that I can show you here that's slightly different as well, let me just kill this off. So I'll just switch back to my deck briefly to talk about Spring Expression Language. Spring Expression Language is extremely powerful. We use it in a few different places. And the compilation here it just makes a gigantic difference between performance before. There are some trade-offs and limitations. Not everything can be compiled is the first thing to remember. And well, it's probably easier just to show you. Spell. So I made a trivial class with a foo. I'm using UUID, extra semi, to create a UUID just so I've got some fields to get hold of in the object, right? And then magic spell. That's my little joke. No? Okay. It's a main application. I haven't bothered with a Spring Boot just for this one. I've got a little static method there for doing an out that's just convenient. I'm going to make a batch size of the objects. I'm going to make all of those up front before I do any timing. So I'm making a bunch of foos. So they're objects that are going to get created. And here's my expression. I'm just going to evaluate in these random UUIDs whether the least significant bit of the UUID is greater than the most significant bits of the UUID. So Spring Expression Language has to resolve those two fields and then execute the comparison. And here's my evaluate method. I've put it in a method. You'll see why in a second. And I am passing the compiler mode, this new feature, programmatically. There's a -D switch that you can use to turn this stuff on and off, but I'll do it programmatically here so you can see the difference. So I pass my foo array in. I get a parser configuration. I've got to use the class loader because it's going to do some stuff with bytes. And make an expression parser that uses the configuration. get a valuation context, make an expression of the string. Here's my stopwatch. It's a pretty output. There's a note to say we're about to start evaluating the expression, and there's a stop. I'm going to print the output here. So with the compiler mode off, I could do with that font being bigger. Never mind. Console. Fixed width and tab width.
No, you want to go to fonts.
Fonts again. Yay. Let's kill that. Die. Where's my alarm gone? There we go. So there we go. It doesn't take very long to run, but it tells us exactly how long it took to evaluate that expression 1,000,000 times. It took 1.381 seconds. Okay, so JIT makes a difference, so let's get that out of the way first. Let's do this 2 or 3 times and see what happens. Or maybe 4 or 5. So we're shaving a little bit of time off each time. We're getting down to about a second once the thing's warmed up. And now let's try with compilation turned on. Let's run it once just so we can see. Well, fast, done. This is in milliseconds, so it's done already. Like? I think that's good. Clap him, he did it. Put your hand up. I just get to stand here and take the glory. What's the phrase? Standing on the shoulders of giants, that's the one. Okay, so let's run it again a few more times and see what JIT does. Whoa, okay. Like, that's pretty cool. So we're able to use spell in places we weren't able to use it before. It's that simple. You know, we can do quite complex expressions inside the application. We can evaluate hundreds of thousands of these a second and process results on the base of this. Okay. So, how are we doing for time? Oh, not too bad. Half an hour early. What's up next? Oh, too far. So much faster. Simple configuration option. A reminder that Spring integration now re-evaluates those expressions where they're present, and the trade-offs do exist. I'm sure that over the course of time, some of those will get ironed out. There'll be more features, more things that can be compiled. I've certainly talked to a couple of colleagues already today, and I'd be pleased to hear that have said they're going to try and contribute fixes. There's my spell demo. And I thought now I'd talk a little bit about Reactor and show a little bit of the batching code that we're using. It's a slightly more simple version than what we're using in the application, but it would take longer to explain and to run. Reactor provides in the Spring space drop-in replacement for your thread pools and dispatches. So at the lowest level, the difference between using a standard Java util executor and using a Reactor is probably something I should have demoed, but didn't get around to building that this morning. But it's a giant amount of difference. The wait time you have for an individual object being executed between when a worker takes it off the queue is much lower. The resource utilization overhead is much lower. And in our application, when we started switching standard executors out for Reactor-based ones, we saw the resource utilization drop from 80% of CPU on the Acorn machines we were testing on down to between 5 and 10%, just when we were able to make sensible adjustments about the thread pools. The Reactor UDP, TCP servers and client, much faster again. They use the same basic stuff under the hood. And we're using the Stream API for batching some other functionality, and we're embedding all of this inside Spring integration components. And there's a plug for the Building Reactive Applications talk, which is tomorrow morning. I don't know which room that's in, actually. John? Is it in here, or is it ballroom? Ballroom. Yeah, you should go to that one. So the batching endpoint code. So, same demo. In this case, I'm going to try and fire some data to a rabbit running on the same machine. It's going to go a bit slower because we're going to be chewing CPU in a bunch of different places. It's the same TCP server, same one, same blob of code, and same counter. Well, actually not using the counter, but here's our simple batcher. The batcher goes in integration on the end. It's just on the end there, and the batcher itself, this time we're just going to send straight to a RabbitMQ instance. We're using AMQP, Spring AMQP, the Rabbit template there. Got a couple of counters in there, and we've registered a converter. So we build a batch using this stack of code here. So where before we had 10 or so lines of Reactor TCP server code, here we've got 10 or so lines of Reactor Streams API code. So we create the deferred in this version of Reactor is kind of the entry point. So you'll see down here, here's my deferred. This object isn't a message producer support based object, it's an integration object support, but it implements its message handler, so we can wire it onto the end of a channel. The channel feeds the handle message object, and I've got a little hack in here so I can send one message to it at a time and just have it directly send to the output channel, which with a bit of luck it'll show how slow that is compared to sending the batch. And other than that, I'm simulating the list production because the converter that sits inside the RabbitMQ, the Rabbit template is expecting a list, so I've got to send it a list even if I'm sending a single event. I've already set up the Rabbit template to pick the queue, the exchange and the routing key. So there we go, there's some Rabbity stuff there. Message converter, there's the Rabbit template, there's the exchange.
Stuart, the converter just creates a big byte array with a length limit?
Yep, reverse serializes. So the question was, does the converter just create a big byte array? So the RabbitMQ message it prefers to get a blob of bytes to go on the wire, so we need to help it from sending a list of byte arrays to get a single blob of byte arrays. It's this fairly simple message converter. So this is Java 8, this is what this is doing. I'm just going to comment this out, and then I'm going to show you the longhand of what the consumer is doing. Oh, no. Wrong one. Add implemented methods. So it's a consumer. If you're familiar with Java 8 and the reactive stuff, you'll know this is pretty common. And inside here, I'm taking advantage in this block of another feature of Java 8, the Streams API, just to iterate the list of messages. So I need to switch from a list of message objects to a payload that is the list of payloads. So I'd do a for loop or something, I guess. Message. And then payloads. This will kind of suck though. So. And payload. There we go. So that's the longhand version of the Java 8-bit. Back to that. So there we go, around. So let's set the batch size to 1. So same ports, again, same file. Simple batcher. Let's find my server, that's my entry point, that's my Spring Boot app. Start from scratch just in case. Start it up. It's over 3. Okay. So this time around, you should see that there is, oh, come on, the batcher. And this time I put a couple of counters in there. Count the batches separately. In fact, that's not going to make any difference this time because it's a batch of 1, but stick it on anyway. There we go, message channel, called input this time, message send rate. Okay, so close that, close that. So we should see that chewing away in a second. There we go. Not very fast, as you can see. Should see something in Rabbit. There we go. Pretty slow. Still not going. At that kind of rate, it's going to take us a while to get through 500,000 events, so I will just kill that one off. 37 seconds. Let's see how many we got through. 25,000, okay. So let's switcheroo. Oh, foo. Where did I foo? That doesn't seem like a fair test, does it? Hit the file system for every message. Let's try that again. I do wish this would remember what you'd picked up before, never mind. So what do we care about here? Counter in. I only guess the rate. We'll just do the rate this time. Oh, which one did I put it on? Wrong one. Both on the same one there. Okay. It still won't be much faster, but at least it's fair. A little bit faster. So the dispatches, it's using multiple threads to do this. So you see it jump up and down as it flicks around the Rabbit, sends a batch. It'll jump up and down for a bit. 18K. Still going to take a while, so stop that off, about the same, 30 seconds. Close it down. And stop. So let's push this batch up. So our payload sizes are in the few hundred bytes to the few hundred K range. But because they're in the few hundred bytes range, it means we can build quite big batches to put them on the wire. We want to try and use the network bandwidth to the best of our ability. We find that we can saturate a 1 gigabit per second network card quite easily with using the same strategy here in Gemfire and in Rabbit. So we do try to do that. Just this one change. Server 3. Okay. I cheated there, I didn't put the graph on first. Bump, bump. Send rate. Oh, you can see it's already faster. It's gone up to 154. Our mean send rate is probably finished, actually. Let's check that. Yeah, it's finished. So in under the time we were doing where we have the interceptor, hadn't done anywhere near as much. It's already done that much. And it's pretty easy on the far side of the application, either in Rabbit or in Gemfire, to deserialize a blob and batch it. The deserialization cost we found is much, much, much lower. It's orders of magnitude lower to do that unpacking on the far side of the network. And again, I think that's one of the things that John's going to talk about later this afternoon. Let's just run it one, maybe two more times, and we'll see if it brings the time down once the JIT's warmed everything up. "11 seconds, much better. One more time. 1 second. So over time, we go faster, that's the gist of it. Once the application's warmed up, we can quite comfortably do in the range of hundreds of thousands of events per second. Okay. So here's my summary. I'm going to be a bit early, so maybe some questions. Spring integration is much, much faster than it was a year ago. Good performance is a huge benefit to you in more than one way. Better resource utilization. If you're running in the cloud, this is a huge cost saving, potentially. And batching payloads is the other big takeaway here. If you can batch when you go near a network or near any kind of I/O, any I/O boundary, then you will see significant performance improvements. There is a little bit of a trade-off there. If you're holding data in memory in a batch, then you either have to find ways to use it to put this data somewhere temporarily in a reliable place, but then you're likely to incur overhead. If you need to make a copy of it and put it on another node, then you're going to the network again. If you need to put it on the file system, you're going to some other output. And basically Reactor for the win. Reactor has helped us go a long way here. Okay, I will now take questions.
Is there any way that you're using or applying back pressure to prevent like different nodes from being flooded?
So the question is, are we using back pressure to prevent different nodes from being flooded? And the answer is yes and no. Yes, originally the architecture we had applied back pressure right the way up through the system, but we found that this actually didn't help us a great deal because it meant that we pushed back pressure right the way out to the network sources. So they would see us going slow, and they have their own strategies for dropping data and avoiding being slowed down by us. We've moved a valve effectively into the system so that we can decide when if we have back pressure, so we can drop data there. But ultimately, at these types of rates, and if we see a microburst that we can't cope with, the only thing we can do is throw data away in order to keep the system alive. That's the safest strategy for us. We've looked at a few different things in Reactor and the batching strategies. The latest versions of Reactor have immediately before the hard ring buffer, the fixed size ring buffer, there's a soft queue. So there is a bit of leeway there for, that gives some flow control. And the reactive streams initiative that the Reactor team here is part of with Netflix, TypeSafe, Red Hat and others, the reactive streams APIs, and that team is actively working on flow control and back pressure to be part of the API functionality. So this will come through the reactors. So, we'll be able to use that when that matures in the support. But the bottom line is we can only really absorb that for small periods of time. Ultimately, you have to make a decision. If you're backing up the system and or some downstream system of you is backing you up, you've got to make a decision about whether you're going to throw data away or not. Hello.
I'm guessing that the spell expressions you were trying to optimize are primarily in the filtering stages of your Spring integration?
No. Our filters right now are a bit more complicated, and we decided to implement those manually. We'll go back to using spell-based ones at some point, I hope. But actually, most of the expressions are, well, in two places. The output to file is in CSV form in one option, and And the CSV format, we're using Spell to configure that against each event object. So you can you can specify the fields you want or subfields, and Spell does that evaluation. And it's metrics, calculations, expressions. So some of the analytics we're doing on these events look at numbers of different fields. So in order to understand a given status, the status is really a combination of looking at those fields. So you have to evaluate the values of each field in different places in different protocols. So the expressions can be quite complicated. Hello again.
So you pinpointed generating the UIDs as a performance bottleneck. How did you go about figuring that out? How did you profile that to discover that?
Well, I stuck your kit on it, and your kit showed me exactly what was going on within a couple of minutes. Yeah. We could see it in Visual VM as well. Well, not everybody in the team uses your kit, but we could see it in Visual VM. You can just see it in the stack trace and the sampler immediately. Yeah. Anybody else? Hello?
You say to optimize the batch size?
Say again, sorry?
Batch size?
How do we optimize the batch size?
Yeah. When did those two
Good question. So what we're hoping to move towards is some kind of adaptive batching, so let the system decide. But right now, it's a case of iteratively testing. We put it on a live feed of data, and we threw data at it. We gave a batch size that was too large and a timeout that was too short, and we figured out where it wanted to settle. And then we give it some ability to cope with a little bit of overhead. It'd be easy to tune it to exactly the baseline rate, 100K per second, and then have no ability to tolerate increasing capacity. So no easy answer for that one.
And this was, the batching was only a little bit initial for the network hops, was that?
Network into file.
So is there any other benefits like maybe compression or something that go across the network?
Yes, is the short answer.
So when's that trade-off?
I described having 2 data centers. Most of the rest of the application we want on lots and lots of bandwidth. It's just easier for and safer for the application. But when we go over the WAN, we have to look at a number of different strategies for ensuring, because that's a slightly less reliable network, and we can't always guarantee the bandwidth. We try to, but compression's the big benefit there. Yep, absolutely. Did you have another question? You raised your hand a minute ago.
You're using Reactor to provide some level of load balancing, I guess, but prior to implementing it, did you have
Yeah, I kind of skipped some of the iterations we went through, but we used thread pool executors and tried to tweak those. We used a single one for all of the different protocols and tried to balance the work out across all of the workers on the different protocols, and we came back to running on individual protocols in the end. But we made some guesses early on about where we could benefit from seeing both Reactor-based task executors and standard Java util current ones, and every guess we made was wrong, basically. It was completely counterintuitive under this type of load, we found. Anybody else?
Is compression one of those things that's just there by default, or was that something that you like another Spring integration stuff?
Well, our compression is plugged into the Gen5 1 gateway, so it's not strictly Spring where we do that, but we've implemented our own compression algorithm using Snappy. Yeah, I mean, we could easily do that inside Spring integration. Use a transformer, plug a transformer into, make a batch, make a blob of bytes, put the compression on, and component after that.
Is it more performance, better for performance than
No, I mean, in terms of Spring integration, it wouldn't make any difference. Because of the way we're using Gemfire, we have some code around where the Gemfire edges are in the application, and it makes more sense architecturally for us to do it nearer to Gemfire than less in Spring integration in this case. Gemfire has some batching features already for sending data over to from one grid to another. So we're just trying to take advantage of that. Anybody else? No more? Okay, well, if you, one more time, put all the people who work on the Spring projects, put their hands up, please. Go on, come on. These are the people that have made really this product happen. So I thank all of these people, and thank you for putting up with my my nags, my complaints, my whinges over the last year and a half. These people have done an awful lot of work to make RTI a success. And I wasn't joking when I said I stand on the shoulders of giants to be successful with this product. And they're doing a lot of this work for your benefit. So please don't applaud me when we finish, please applaud them. And that's it, I end. Thank you.